Now that we've drawn Lewis structures, we can use the Lewis structures to help us determine the enthalpy of our reaction. We can do this using bond energies. So the actual bond energies do depend on the atoms that surround it and other factors, but we can make estimates. So we often use the average bond energies to estimate the enthalpy of the change in enthalpy of our reaction. This does work best and gets us closest to the actual enthalpies when all our reactants and products are in the gas state. And bond breaking is going to be endothermic, so we have to put energy in order to break the bonds, which means that our enthalpy is going to be positive. If we are forming bonds, then it is going to give energy off, which means it is going to be negative. So making bonds is going to be exothermic, negative. Breaking bonds is going to be endothermic and positive. In order to determine our total change in enthalpy of the reaction, we're going to add up all of the bonds that we break, and we're going to add up all of the bonds that we form and add those two amounts together. Let's estimate the enthalpy of the reaction for the following reaction, which is methane plus chlorine, giving us chloromethane and hydrogen chloride. We want to find all the bonds that are broken and all the bonds that are made and add up the enthalpies for each. So if we look at our reactants and our products, I see that we are breaking a carbon-hydrogen bond. I'm going to record these. So bonds broken. We have a 1 mole of carbon-hydrogen bond broken. And it's a little hard to see on the table, but on the table, this gives us an enthalpy of 414 kilojoules per mole. We are also breaking a chlorine-chlorine bond. And because we're breaking them, it takes energy, so these are positive values. So all of the values on the table are positive. We just need to remember that when we're breaking bonds, it's positive. When we're making bonds, it is negative. So if we look and we add up all of the bonds that we broke, 657 kilojoules. Now, if we look at the bonds that we're forming a new bond between carbon and chlorine, and we're forming a new bond between hydrogen and chlorine. So the bonds that we're making we're making 1 mole of carbon chlorine. Because we're making it, it's a negative value. And again, these values are coming from that table. It's just the table's a little bit hard to see. 1 mole of chlorine hydrogen, negative 431 kilojoules. So our total would be negative 770 kilojoules for making bonds. So now if we want to find the delta H for our reaction, it's going to be that positive 657 kilojoules from breaking the bonds, plus a negative 770 kilojoules from breaking the bonds, to give us an overall enthalpy of our reaction of negative 113 kilojoules. So this would be an exothermic reaction, giving off negative 113 kilojoules of heat. Now, it is possible that if you want to, you can break every bond and form every bond, and you'll end up with the same answer. It just is a little bit more math for you. So here's an example or a practice for you to try. Pause the video and see if you can estimate the enthalpy of the reaction. So let's look here at the bonds that we have to break. So our bonds that are broken, we're going to have to break our hydrogen-hydrogen bond. We are also going to have to break our oxygen-oxygen double bond. Now, please notice that we do have to break the oxygen-oxygen double bond. You can't just break one because the value for the double bond is significantly higher than double the single bond. Because the double bond is stronger, it takes more energy to break that double bond. So we're breaking a hydrogen-hydrogen single bond. So one hydrogen-hydrogen, that's 436 kilojoules for 1 mole. And we're breaking an oxygen double bond, which is 498 kilojoules. So that gives us a total of 934 kilojoules to break the bond. So now the bonds that are made. Well, we have 2 oxygen-hydrogen single bonds. So if we look for oxygen-hydrogen, it's going to be 2 times, and because we're making them, it's negative, 464 kilojoules. And we have 1 oxygen-oxygen single bond, which is 142 kilojoules. Gives us a total negative 142 kilojoules, I apologize, of negative 1070 kilojoules. So now if we want to find the enthalpy of the reaction, it's going to be equal to 934 from breaking them minus 1070 kilojoules from making the bonds, or negative 136 kilojoules. So this again is an exothermic reaction. If we look up the actual value, so the actual value is negative 136.3 kilojoules. So our estimate is pretty close. If we want to think about the length of bonds, so the distance between the nuclei are what we define as a bond length. And we actually look at the average bond length when we're comparing the bonds. So as our elements get larger, our bond lengths are also going to get larger. So if we look at fluorine, our bond length is pretty small. If we look at iodine, our bond length gets to be larger. In general, the more the electrons that are shared, the shorter the covalent bond. So if we have a triple bond, it is going to be much shorter than a single bond. And this is when we're comparing bonds between like atoms. So we can compare carbon-carbon, triple, single, and double. We can compare carbon-nitrogen, triple, single, and double. And that triple bond is going to be shorter. It is also going to be stronger because we have the attraction for those electrons to the positive nuclei. In general, our bond length decreases from left to right. So as our atoms get smaller, our bond length also gets smaller. And again, we have to compare between similar elements. So in this case, you'll notice we have carbon in each one of our bonds. And so our carbon-carbon bond is longer than our carbon-oxygen bond because oxygen is further to the right. Our bond length increases as we go down the column, and we would expect this because we're adding our valence electrons into higher energy levels, and so they're going to get further from the nucleus, making our bonds longer. In general, as our bonds get longer, they also get weaker. As always, there's some suggestive problems for you to try to make sure that you understand the concepts in this chapter. The odd numbered problems can be found in the end of the book.